Hello everybody, my name is Alexander Beck. I'm an industry manager at Speedgoat for industrial automation, where I make sure that Speedgoat computers can communicate with different types of industrial devices to enable prototyping and testing for typical applications in the automation industry. And that's exactly the topic of today's presentation. I will show you how you benefit from model-based design in the early stages of the product development, and how you can test devices and systems with hardware in the loop against industrial plants. I'll put a main on industrial protocols. I will show you how the Speedgoat machines can be integrated into different industrial communication networks. With the setup depicted here, I want to show you how controls prototyping, plant simulation and testing can be done. Such a setup often just consists of a simulator, the device under test, and a cable. Imagine your plant controller communicates with a motor controller or an I/O coupler for analog input-output. It can be equipment from Siemens, Beckhoff, Rockwell or any other vendor. Communication protocols vary from Modbus, EtherCAT to Profinet, as shown in this picture. With a prototyping platform that supports model-based design, you can quickly try new controls and exchange data with devices on the field level. This is often referred to as rapid control prototyping, RCP. Or you use it as a simulator of an industrial plant in order to test the controller. This workflow is typically denoted as hardware in the loop testing, HIL. Testing use cases in industrial automation are manifold. Let me give an overview. It shows the two prominent cases RCP and HIL and corresponding subcases. With RCP, you develop new controls and test them by driving real actuators like motors. This can be done on the control level of the plant, where the target machine acts as a programmable logic controller, or on the field level, where the target machine is directly exchanging data with sensors via DIO and AIO. The other way around, hardware in the loop, lets you test single devices or systems by simulating the parts of the plant the device under test is typically connected with. You test human-machine interfaces, programmable logic controllers, or devices on the field level. As we move on in this webinar, I'll present customer examples and will refer to that overview again. Building a setup for testing a PLC also allows you to test algorithms for prediction and lets you perform virtual commissioning prior to the on-site acceptance. Such a setup also works out pretty well for the training of operators and serves as a demonstrator to show around the plant's future operation. To give you an idea of what such a testing scenario and demonstrator could look like, I will illustrate how Nabla, one of our customers, applied the HIL approach for testing tunnel control systems. They use Simulink to create a digital representation of the physical tunnel, especially the tunnel automation system, including the devices for lighting, ventilation, and fire alarm. Then they were looking for real-time testing solutions in order to simulate in real time, connect to the tunnel control system, and test it. They deployed the tunnel model to a Speedgoat real-time target machine that turns the machine into a digital twin of the physical tunnel. The simulator connects to the tunnel control system via Profibus and simulates the communication interfaces of all devices that are actually part of the tunnel automation system. As a result, this setup allows Nabla and their clients to test the PLC application without a real tunnel and long before the final commissioning takes place. This minimizes implementation risks and reduces the efforts and resources during the final commissioning, like time, manpower, equipment, and energy. This is a schematic representation of what Nabla did. The real tunnel automation components communicate with the control system via Profibus. The digital twin of that plant made with Simulink runs in real time on Speedgoat hardware, still connected with the real PLC, but now not in a tunnel, but on a desk. So besides normal operation, they can now conveniently test borderline cases that are expensive, difficult to reproduce, or even impossible in a real tunnel. A graphical user interface was created to control the tunnel simulator. Together with the operator system, the setup also serves as a demonstrator and training tool. The real setup looks like this. We see the Speedgoat machine with a series of green lights, one light for each of the 54 simulated Profibus slave devices. The PLC on the right is the Profibus master and the device under test. With such a setup, Nabla can now show correct tunnel operation to their clients months or even years before the real tunnel is ready for the installation of any automation components. Let me quickly show you how to set up such a Profibus device simulation in Simulink. Imagine you are writing code for a Siemens PLC using TIA Portal. In real life, your PLC is connected with the Profibus I/O coupler that captures data from connected sensors. In this example, the coupler is just equipped with a 2-channel analog input module that is configured for voltage measurement. The device sends the analog values to the PLC where your control algorithms further process them. Once you write code, you have to test it, how the code reacts on events like the voltage is continuously zero, the voltage exceeds a limit, or the signal noise is too high. A standalone PLC on your desk, which has no connection to any device, can only be used to check if your application can basically be started. But once you connect it to a simulator that emulates the remote Profibus interfaces and simulates the signal behavior, you can test your PLC application state machine, error handling, and control algorithms. You can do that manually or in an automated way. Let us simulate the I/O coupler and its analog input module. In Simulink, you generate a sine wave for the voltage that is measured on the first channel of the analog module. You send it together with the second channel signal to the PLC with the help of the Profibus send block. Before, you define the address of the simulated device in the network according to the address defined in the PLC project. This allows the PLC to find the device in the network. Furthermore, you import the related device description file to set the device identity and some other properties needed for Profibus communication. After building and downloading the model to the Speedgoat target machine, which is now connected with the PLC in place of the I/O coupler, the communication between the simulated device and the PLC gets green. The PLC receives the voltage signal and you can now monitor the signal curve. But that's not all. You can now individually change the voltage signal in Simulink and basically all the other signals the PLC actually receives from the devices of the plant. This allows you to test your PLC code in normal operation, edge cases, and in fault situations. With such a setup, you benefit from all the advantages that the model-based approach provides for implementing and testing new software and hardware within the product development process. This refers to trying new things with rapid control prototyping in the early development stages and validating controls, devices, or systems with hardware in the loop testing. You get the best overview of RCP and Hill and their benefits by watching the webinars of my colleagues Daniel and Timo. Timo has also included great workflow demos that demonstrate specific MATLAB features, such as signal monitoring, automated testing, and instrumentation by building custom graphical user interfaces. Prototyping, simulation, and testing are valuable on all levels of automation plans. The different levels are well illustrated by the so-called automation pyramid. On all levels, new components are developed which must be tested against other components. Such components are sensors and actuators on the lowest level, controlled by programmable logic controllers on the next level, followed by operators and monitoring systems on higher levels. Sure, there are planning systems on the factory and the company levels, such as IT systems for warehousing and shipping, and at some point we will end up in the industry cloud. But I won't cover this today because the importance of deterministic, or one could say hard, real-time decreases the deeper we get in the pyramid. So the closer we get to the sensor level, the more you benefit from real-time simulation and testing. The model-based simulation and testing approach along the levels of the pyramid can be applied to multiple industries, since we find many similarities like network topologies, protocols, and devices. Therefore, whenever you want to prototype or validate things, you benefit from real-time simulation and testing with Simulink and Speedgoat, no matter if you are dealing with electric power, heavy machines, intelligent homes, ships, assembly lines, traffic, industrial equipment, or oil and gas. Before browsing through more use cases, let's take a look at the equipment that is actually needed for prototyping, simulation, and testing. A typical setup looks like this. On the development computer, you use MATLAB and Simulink to develop model-based designs of plant controls and motor controls. You model and simulate state machines and plant dynamics. You can even create models from measured data. The Simulink real-time workflow lets you build real-time applications from the model and deploy to Speedgoat real-time target machines. Finally, during runtime, you change parameters and monitor signals from your host computer, and you can run interactive and automated tests. For this purpose, you can also create graphical user interfaces. Speedgoat offers machines of different performance classes and form factors. You use a unit machine to simply control a stepper motor, or you order a rack if additional hardware is required to build a complete hardware in the loop scenario, for example. The target computer combines CPU and FPGA technology. Automatic C and VHDL code generation allow you to deploy parts of the model either to the multi-core CPU or to one of the FPGA modules installed in the target machine. You do that to achieve faster and more deterministic execution of your algorithms, and also faster communication to whatever industrial equipment is connected. And talking about the interfaces to external industrial equipment completes the overview of the typical setup. The real-time hardware is connected either with sensors and actuators on the field level, or with higher level controllers and monitoring systems, depending on the use case. For that purpose, Speedgoat provides a huge range of I/O modules. In addition to the programmable FPGAs, there are countless configurable I/O modules and those with fixed functionality. In addition to the classic analog and digital data input and output, the following protocols supported by Speedgoat hardware are relevant in industrial automation. Protocols like NDAT, SSI, and BIS are used to interface encoders, resolvers, and sensors. In addition to basic serial communication with RS-232 and others, there are classic field bus protocols such as Profibus and CANopen. As the serial communication is a bit outdated, modern communication is Ethernet based. Typical protocols are EtherCAT, Profinet, Ethernet IP, and PowerLink. Yeah, and they are mainly used for the communication between the PLC and the field devices. The communication to higher level controls and monitoring systems is not that time critical. Therefore, protocols like Modbus, TCP, and OPC UA are widely used here. Each module comes with driver blocks for MATLAB and Simulink, enabling the module configuration and the transfer of process data. So now we are prepared to connect to industrial equipment. Therefore, the following slides show Speedcode real-time target machines connected with typical devices, highlighting the capabilities of the respective interface. Speedcode machines support can open master and slave and allow transmission rates of up to 1 Mbit per second. Here, as an example, the target machine is connected to a can open slave from Vago, equipped with some input-output modules for analog data. Profibus master and slave is also supported. On the left, the master module of the baseline machine is connected with the slave device from Vago. The Siemens PLC on the right acts as a master and is connected to the Profibus multi-node simulator, which can simulate up to 128 slave nodes and is therefore suitable for plant simulation. This picture shows a connection with what is probably the most common EtherCAT slave device, the EK1100. Using EtherCAT and distributed clocks enabled, users can achieve precise synchronization and bus rates of 8 kHz or more. For Profinet, the picture shows the connection of popular devices from Siemens. On the left, the master interface of the baseline machine exchanges data with the ET200SP, I guess the most commonly used Profinet I/O coupler for signal input-output on the field level. And on the right, the S7 1500 PLC communicates with the mobile machine, simulating 32 slave nodes. Similar to Profibus, this multi-node simulator can simulate up to 128 Ethernet-based slave devices. Profinet offers synchronous communication with update rates of 4 kHz. The best edited image belongs to Ethernet IP, the protocol mainly used in North America. Here again, the multi-node simulator simulates up to 128 adapter devices connected with an Allen-Bradley PLC on the right. And on the left, on the other side, Speedcode's Ethernet IP scanner interfaces can connect to remote Ethernet IP adapter devices, such as this Allen-Bradley I/O coupler shown here. Speedcode target computers also support PowerLink. The control node interface can easily be connected with B&R PLCs. The most accessible protocol is Modbus TCP. The Siemens PLC on the left acts as a Modbus client, reading and writing signals provided by the servers that the unit machine simulates. The motor controller from Nanotech on the right acts as a server and provides data for reading and writing to the baseline machine, acting as the Modbus client. Some protocols are supported with pluggable I/O modules, some others are supported with the onboard Ethernet adapters. This allows the simulation of multiple protocol nodes, especially for the purpose of I/O simulation, plant simulation, and hardware-in-the-loop testing. Protocols supported, for example, are Modbus TCP and OPC UA. OPC UA is an object-oriented Ethernet protocol where one client exchanges data with multiple servers. A server manages all its information in a structured node tree. Nodes can be objects, sub-objects, variables, methods, events, and alarms. A client does not simply read data points. Instead, the client triggers services like calling a method, subscribing to an event, putting a file, reading, or browsing through the namespace. Every item has a name, so addressing with OPC UA is not index, but name-based. And that's a completely different approach to the more or less flat and address-based communication with typical industrial protocols. OPC UA is often used for the communication between PLCs and supervisory systems, and that's the point where hardware in the loop testing comes into action again. Imagine your HMI controls and monitors a plant by exchanging data with a plant controller. Your HMI application manages a bunch of pages with tables, parameters, sliders, and graphs, and operates depending on the type of the plant, its version, and the data the PLC provides. Then I'm sure you want to test this application prior to the on-site commissioning of your plant. To give you an idea on how you can simulate what the HMI is usually connected to, I prepared a short demo about the usage of the OPC UA blocks in Simulink. For that purpose, I've taken the tank example that comes with MATLAB and added OPC UA server blocks to make the parameters and signals public to connected external OPC UA devices. The hardware setup looks like this. The tank model is deployed to the target machine and provides data on the OPC UA server interface. The OPC UA client is a computer with UA Expert installed, a very nice client tool that serves as a kind of human-machine interface. The client connects with the server interface, reading and writing signals and parameters. Let's switch to Simulink. The setup block is used to define the local IP address. The node blocks add variables and objects to the server's node space. The area block, for example, represents a parameter, and the height block adds the OPC UA node height to the node space and cyclically updates its value. And finally, this block makes the tank dynamics subsystem an OPC UA object in the resulting node tree. So this object will contain the area parameter and the height signal being subnodes in that object. Once the model is running on the target machine, OPC UA clients can connect to the OPC UA server interface and access the nodes defined. This tool from Unified Automation serves as such a client. You can browse through the node tree, you find the tank dynamics object, and can read the actual tank height, which already reached the limit of 10. Before connection, the client knows nothing about the nodes of the server. Even things like data types, engineering units, and the time the nodes were last written, they all are properties that can be read by the client during runtime. So from here, we can do the same as the original model was intended for. We simply let out whatever is in the tank by writing the corresponding OPC UA node. We can still monitor the tank height and can also speed up the process by writing the flow rate. So much for the product portfolio. Let's now come back to common use cases for real-time simulation and testing. I will now touch on the highlighted cases, illustrating each topic with a user story or a demo. The most concrete and widespread use case with RCP is motion control. Motion control is quite popular in academia. With motion control, the target machine communicates with one or more motor controllers to move whatever is attached to the motors. CANopen is just an example on how to connect even through CANopen, and EtherCAT are often requested for this kind of application. I prepared a short demo showing the general workflow to implement such a setup. In this demo, the model running on the Speedgoat machine controls a motor controller from Nanotech, which drives a stepper motor. The Operating mode is position control. That means the motor controller receives the position set point via Modbus TCP, turns the motor and sends back the current position. Modbus TCP is an Ethernet-based protocol. Both Ethernet adapters are connected via a standard Ethernet cable. The motor controller acts as the server and is configured by a vendor-specific tool. The Modbus TCP client interface of the Speedgoat machine is completely configured from Simulink. In the Simulink model, you use the setup block to set the IP address of the local Modbus client in the network. You place a connection block to tell the client the IP address of the remote Modbus server, the motor controller. With Modbus communication, data is encoded in so-called registers. According to the manual of the motor controller, you configure the transceiver block to write a specific amount of registers to a specific address, and you use the byte packing block to pack the signals the motor controller requires for operation. These signals have different types and start with a control word that triggers the transitions of the motor controller state machine to finally reach the operational state. To build that signal, you can use Stateflow or go the easy way by just using the signal editor block. That allows you to define the signal curve with the help of that graphical editor, with a table, or you can also import data directly from MATLAB. According to the motor controller manual, you must set a specific bit in the control word to trigger the move command. Then you continue packing the remaining signals into the Modbus registers, the mode of operation, the position, and finally the velocity. As the motor controller CPU expects the data in big endian format, you must swap the bytes of the Modbus registers using the byte reversal blocks. Dashboard controls enable you to control the motor directly from Simulink during runtime, a button for the move command, and sliders to change the position and the speed. The receiving side is pretty much the same. You read registers from a specific address, you decode the data according to the motor controller manual in order to get the status word, the actual mode of operation, the position, and the motor's velocity. One specific bit of that status word tells you when the motor has reached the commanded position. Once you build the real-time application and run it on the Speedgoat target machine, you can monitor the received signals in the data inspector. The current position, the velocity, and the position reached bit. Furthermore, you can instrument the application using the dashboard controls. Sure, you can simply turn this little motor to the left and to the right, but you could also add a second motor for positioning an XY table. You could control 5 motors of a powertrain test bench with 100 kilowatt each. And you can connect with robots and tackle positioning tasks. All that directly from Simulink. Engineers who want to develop complementary controls in parallel to the plant controller follow the bypassing approach. This is convenient for system retrofits when trying new things without changing existing hardware and software. The Speedgoat target machine acts as an additional controller that performs a completely new function parallelly to the PLC. This can also include testing new sensors exclusively connected to the prototyping machine. Adopting the Simulink real-time testing workflow, users can take advantage of Simulink capabilities for modeling, tuning, and optimizing new designs for running plants. That's exactly what HOMAG did when they developed their latest generation of woodworking machines. They experimented with a new heating unit and wanted to prototype the corresponding control algorithm using Simulink. The Speedcode machine receives data from the field, runs the heating control algorithm, and sends command values back into the field via the PLC. And all the communication is done using the EtherCAT communication protocol. Well, I would like to demonstrate how one can configure such an EtherCAT interface in Simulink. The unit real-time target machine simulates a motor controller that receives speed set points from the EtherCAT master and sends back the actual speed. Instead of a real PLC, I use Beckhoff's TwinCAT runtime, which turns a Windows 10 computer into a PLC. The standard Ethernet adapter of that computer then functions as the EtherCAT master interface. In Simulink, you use the EtherCAT slave blocks to configure a custom slave device to exchange data with the remote EtherCAT master, the PLC. You define the process data objects that the master should read and write. If you want to simulate a simple motor controller, typical input-output signals are the control word, the command speed, the status word, and the actual speed of the motor. You could use Stateflow to program a state machine for your simulated device, but this example just delays the received control word and sends it back as the status word. The simulated motor, the controlled system, is just a simple PT2 element that delays the command speed and adds a slight overshooting. Let's take a look into that subsystem. It's completely made up with standard Simulink blocks. That's all you need to do to set up the slave device. Finally, you export the EtherCAT slave information file for further use in the PLC configuration tool. It's TwinCAT. TwinCAT is used to configure PLCs from Beckhoff. After importing the ESI file, you can add your slave to the network configuration and tell the PLC to connect with that device. The PLC can then read and write the remote process data objects that you defined in Simulink. The PLC code computes the control word depending on the status word received. The commanded speed is a pulse whose amplitude toggles between 0 and 100. After mapping PLC input-output variables to the EtherCAT variables, the PLC application is ready to exchange data with the remote EtherCAT device and can control the simulated motor controller. After building the model and starting the real-time application on the target machine, both devices start communicating with one another. You can see the speed signals in the data inspector. The commanded speed, the one the model receives in red, the actual speed, the one the model computes in blue. Sure, you see the same on the PLC side. You add the respective signals to the scope and can then monitor the speed dynamics. As described with the user story, such a setup is quite convenient when you want to add complementary controls to an existing plant. And as illustrated by this short demo, such a setup can also be used to simulate a specific device in order to test the controller, a PLC application, for example. Once a controller needs to be validated, engineers leverage automated PLC testing, which allows testing of the PLC application in normal operation and under fault conditions by simulating the rest of the plant. PLC testing is the most common use case for commercial customers. I already introduced PLC testing by talking about tunnel automation at the beginning of my presentation. Now I want to close the topic and the webinar by illustrating how prototyping on the one side and testing on the other side can be combined to a seamless development workflow for plant controls. In many cases, the PLC's only interface to other devices is just one Ethernet cable for commissioning and instrumentation, communication to field devices, and communication to monitoring systems. As a result, a hardware-in-the-loop setup is often just made up of the PLC, the target machine, and a cable. The Speedcode machine completely simulates the behavior and interfaces of all communication partners. Testing can then be done manually using self-written graphical user interfaces or automatically using MATLAB scripts, external test automation software, or Simulink Test. Such a solution enables testing during the development. When writing the PLC code, it enables testing of the actual operation as well as error cases. Tests can be repeated, which makes results reproducible. I once explained PLC testing in a webinar. Find the recorded session in Speedcode's Knowledge Center. I used the mobile real-time target machine and equipment from Siemens connected via the Profinet communication protocol to illustrate the basic workflow for testing a programmable logic controller. The demo setup looked like this. In the real world, the PLC communicates with a motor controller which drives two motors. A control panel with switches, some LEDs and a potentiometer communicates with the PLC via such a Profinet I/O coupler. After demonstrating the actual operation of that setup, the PLC gets disconnected from the real devices and connected with the simulator. The simulation then takes over the function of the real devices and fools the PLC into thinking that it is operating in a real plant. For example, this control box is then represented just by a graphical user interface in the host computer. Let me complete PLC testing. This slide shows the combined use of RCP and Hill. In addition to the classic languages of the IEC 61131 standard, today's PLCs can also be programmed with Simulink. In addition to vendor-specific solutions for C-code generation, the PLC coder for Simulink can be used to generate classic PLC code like structured text, function blocks, or ladder. If the controller and the controlled system have been developed in Simulink, they can be tested directly in Simulink with model-in-the-loop techniques. When it comes to hardware, inter-device communication and real-time, the PLC code can be deployed to the PLC as a production code. The remaining parts, the plant simulation mainly, can then be deployed to the simulator with Simulink real-time. The advantage of such a development approach is that the controller application and the plant simulation grow closely interlinked from the very beginning. As soon as the application is tested on the real PLC, the simulation model for hardware-in-the-loop testing is ready, and this saves time. That's all for today's demonstration. Before finishing, let me quickly summarize the benefits of RCP and Hill. You quickly develop accurate motion applications. You replace traditional testing methods for PLCs with hardware-in-the-loop testing to deliver high-quality controller software. You apply model-based design and real-time simulation to all stages of your product development process and unite software design and testing. And finally, you experience convenient workflows for tuning parameters, monitoring signals, and optimizing your code. I hope you got an idea of how model-based design, simulation, rapid prototyping, and hardware-in-the-loop testing can be applied to the different applications in the automation industry. Many thanks for your attention.
You want to learn more about real-time controls testing? Then find additional content linked here.